Hello and welcome to this presentation on comparing fourth and the fifth generation district heating and cooling with a case example of a network in Rome in Italy. District heating is recognized as an effective solution for decarbonizing building heating demands and provides stable and affordable heating. This has led to a renewed interest and growth in this sector, particularly in Northern Europe, where the fourth generation of district heating is seen as the future-proof solution. In recent years, the technology has also been gaining momentum in Southern Europe. It is, however, a question how the cooling demand in the Southern Europe may impact the optimal network design. This has led to active search for solutions within the district heating space and a partial merger with individual heat pump solutions in the form of the fifth generation district heating and cooling concept. However, as the fifth generation is to a large extent an individual-based supply system, it is losing out on many of the benefits the fourth generation offers. This presentation focuses on the economic comparison of fourth and fifth generations, fulfilling both heating and cooling demands in Rome. For generating realistic heating and cooling demands, we used NC Plus, the model tool, to model typical new and existing 6 flat multifamily buildings. The heating demands were simulated for a comfort temperature of 20 degrees for the and cooling temperature of 22 to 26 degrees. When viewing the annual demands, it becomes clear that while there is no synergy between space heating and cooling demands, there is a good daily synergy between the domestic hot water demands and the space cooling demands. In the case of new multifamily buildings, the daily synergy potential is approximately 97%. In addition to the multifamily buildings, we made models for new and existing single-family buildings. And the graphs shown here are based on a standard Italian cooling operation corresponding to an indoor temperature of 26 degrees. And as with the multifamily building, there is a relatively good synergy potential between the domestic hot water demands and the space cooling demands, particularly in case of new buildings. In an effort to see the impact if the comfort cooling temperature would be lower, a new simulation was performed, where the comfort temperature was set at 24 degrees. And the increased comfort level leads to increased waste heat and lower synergy potential. For instance, the synergy potential for existing buildings goes from 62 to 56%. And in new building, it goes from 92 to 82%, which of course is still a good synergy potential. In this study, we compared two fourth generation and two fifth generation variants, as shown here. The fourth generation variants are identical in respect to the heating demands, but differentiate on how the cooling demands are fulfilled. In the fourth generation district heating and cooling variant, the cooling demand is addressed using a cooling module, which is an add-on on the substation. The waste heat from this cooling operation is prioritized for fulfilling local domestic hot water demands, and any excess waste heat is injected into the district heating system. In the second fourth generation variant, the cooling demands are met by individual split units. As for the two fifth generation variants, we have a high temperature variant, where the operating temperature is maintained at a level that is favorable to for a heating mode operation of the building level heat pumps. And to avoid excessive heat losses in this variant, it is designed with an insulated distribution network. And we have a low temperature variant with operating temperature around the ambient soil temperature. And for this variant, it is assumed that the heat pump is only needed for fulfilling space heating and domestic hot water demands, and that the cooling demand can be fulfilled directly by the district heating grid. Before we come to the techno-economic results, I want to mention that there is a general challenge with these types of studies, which is to ensure transparent techno-economic data. For that purpose, the study is relying on data from various sources. We have the technology catalogs from the Danish Energy Agency. We have a lot of information from the Danish district heating utilities. We have information from Danfoss products. And we also use statistics on energy cost and purchasing power parities from Eurostat. While there will inevitably be uncertainty in the cost estimates, it is assumed that these uncertainties are similar across the different network concepts that we are comparing. The comparison is made by comparing the total annual cost of heating. That is, it includes the analyzed cost of investments, cost of maintaining the system, and the cost of the input energy. As for the central heat generation, we minimize the investments in the central plant by differentiating between the base load and the peak load. In this situation, when there is more waste heat from cooling operation than can be consumed by the end users, we assume it's dissipated into the air by the utility, so we use the network. We further differentiate between multifamily buildings in the fourth and the fifth generation variants, as flat level heat pumps would simply be too expensive. And therefore we have made the assumption that in the fifth generation systems, a basement heat pump is applied. This significantly reduces the end user heat pump costs in the fifth generation systems. We have further neglected the additional cost of riser pipe, manifolds and heat meters in each flat in the fifth generation multifamily buildings. Further, the heat or the cool loss from these extra building pipelines are neglected. For the fourth generation variant, we decided to go with flat stations in every flat and the cooling module accordingly, which in comparison to a central based equipment is a more expensive alternative. Now let's dive into the results of the analysis, and we start by looking on the annual cost for the normal energy year scenario. The graph to the left shows the total annual cost for single family buildings, and the one to the right shows the total annual cost for multifamily buildings. What we can see is that in all cases the fourth generation variants are more economic than the fifth generation variants. Now, by breaking up the cost, we can identify the key economic differences between those variants. Firstly, the largest difference is in the building level capex, where in the single family buildings the fourth generations are much more cost effective. In the multifamily buildings, we need to keep in mind that we are not comparing identical solutions, as the fourth generation apply flat stations, while in the fifth generation a basement level heat pump is applied, and that we ignore the additional cost of the pipes and the riser pipes. Secondly, the building level energy costs are by nature much higher in the fifth generation compared to the fourth generation. And this is normal, as large part of the heat generation is taking place in the building in the fifth generation. Thirdly, we can look on the district heating network capex, which includes the distribution network and service pipes. What we can see here is that the analyzed distribution cost is rather similar between the different network variants, with the uninsulated fifth generation pipe network slightly cheaper than in the other variants. Finally, we can consider the district heating heat generation cost, which includes the heat generation plant investments as well as the input energy cost. As expected, the district heating heat generation cost is much higher for the fourth generation than the fifth generation systems. But let's also look on a crisis here. When we increase the energy price levels corresponding to what we saw after the start of the Russia war on Ukraine, we can see that even if that would be a permanent condition, the fourth generation are much more cost effective. But what is more important to consider is that in a properly designed fourth generation system, alternative heat generation plants would be applied, along with the heat pumps, exactly to navigate varying energy supply situations and to increase system resilience. This would be much less effective in the fifth generation systems, as most of the heat generation is performed at the building level, where there are no possibilities to change the supply system. As for the potential next steps of this study, it would be natural to investigate some typical aspects of traditional district heating systems. For example, the potential impact a central thermal energy storage could have on the system operation and economics, particularly if the heat generation would be operated in respect to the power spot market prices, as well as if balancing services would be offered to the power sector. It could further be interesting to explore some alternative heat sources, particularly waste heat sources with medium or high temperatures. Now, it would also be good to extend the number of buildings and end user types beyond the current 4 types of residential buildings. At last but not least, it would be interesting to team up with a partner in Southern Europe who could provide more details on local technology cost levels. This concludes my presentation, and I thank you for your attention, and I welcome all questions.